Welcome to the last episode of AP Computer Science. It's been real, and as always, be sure to have your writing utensils handy to take notes. A hashing scheme involves converting a key piece of information into a specific location, thus reducing the amount of searching in the data structure. Instead of working with the entire list or a tree of data, the hashing scheme tells you exactly where to store the data or search for it. One important barcode system used by retail stores is the UPC-A code, which involves a sequence of 10 digits. The system provides 10 billion different possible products. For quick access, an array of 10 billion locations would be nice, but wasteful in terms of computer memory. Since it is unlikely that a store would carry such a huge number of items, a system is needed to store a list of products in a reasonably sized array. A cash register using a barcode scanner needs a very quick response time when an item is scanned. The 10-digit barcode is read, the item is searched for in the store's database, and the price is returned to that register. While searching algorithms for the order log2n are relatively fast, we may want an even faster algorithm. Suppose hypothetically that a store maintains a database of 10,000 barcodes out of the possible 10 billion different values. The values are stored in an array called a hash table. Because an array has a direct, random access to every cell, using a hash scheme will be much faster to access the desired item. The hash table is usually sized about 1.5 to 2 times as big as the maximum number of values stored. Therefore, the store will need an array with about 15,000 locations. A hashing scheme tells us where the item is stored. A hashing algorithm is a sequence of steps, usually mathematical in nature, that converts a key field of information into a location in the hash table. These key-to-address transformations are called hashing functions or hashing algorithms. When the key is composed of character data, a numerical equivalent such as the ASCII code is used so that the mathematical processing can take place. Barcodes are numbers, so a conversion is not necessary. Some of the hash functions are division. The key is subject to integer modulus, equal to or slightly smaller than the desired size of the array. The result of the division determines which short list to work with in the hash table. Mid-square. Key is squared and the digits in the middle are retained for the address. This probably won't work well with barcodes because they are such large numbers. Folding. The key is divided into several parts, each of which is combined and processed to give an address. For example, if this is the barcode, then first group into pairs. Then multiply the first 3 numbers together. Add this number to the last 2. Then, the remainder of module division by 14,983, which is the largest prime number less than 15,000. The address 7133 is the location to store barcode 70662-11001. Finally, in the address 7133, there will be stored all the fields related to this item, such as the price and the name of the item. It is important to develop a good hashing function to avoid collisions in the hash table. Even when using a prime number for the divisor, it is possible for 2 barcodes to result in the same address. To reduce the chance of such a collision, the hash table size will be about 1.5 to 2 times bigger than the number of expected items. If the hash table in our example were sized at about 10,000, the likelihood of collisions would be increased. This advanced sizing of the hash table affects the mathematics of the hashing algorithm. Therefore, the programmer must have a very clear idea of the numbers of items to be stored. The number of items must be known in advance, and the number must be fairly constant during the life of the program. This limits the use of the hashing in certain situations. If the number of items is unknown or varies greatly, hashing is inappropriate. There are 2 methods of creating multiple storage locations for the same address in the hash table. One solution involves a matrix, while the other uses dynamic linked lists. To implement a hash table as a matrix, an estimate of the maximum number of collisions at any one address must be made. The second dimension is sized accordingly. Suppose that the number is estimated to be 5. This method has some major drawbacks. The size of the data structure is suddenly increased by a factor of 5. The table will have about 75,000 cells, many of which will be empty. Also, what happens when a location must deal with more than 5 collisions? A dynamic solution, referred to as chaining, is much better. The linked list will only grow when the values are stored in that location in a hash table. In this version, the hash table will be an array of object references. The order of the values in the linked list is unimportant. If the hashing scheme is a good one, the number of collisions will be minimal. After scanning an item at the cash register, the number of steps required to find the price is constant. Hash the barcode value and get the hash table location. Go to the location in the hash table and transverse the linked list until the item is found. Return the price. The number of steps in algorithm is constant. The hashing scheme tells the program exactly where to look in the hash table. Therefore, this type of search is independent of the amount of data stored. We categorize this type of algorithm as a constant time, or O1. If a linked list gets lengthy, it could add a few undesirable extra steps into the process. A good hashing scheme will minimize the length of the longest list. An interesting alternative to linked lists is the use of an ordered binary tree to deal with collisions. For example, a hash table could consist of 10,000 potential binary trees, each ordered by a key field. The hash set and hash map classes are implementations of the set and map interfaces from the Java standard class library. A hash table is used to store their elements. These are the methods for the hash set class. Boolean add adds a specified element to this set if it is not already present. Returns true if the set did not already contain the specified element. Boolean contains returns true if the set contains the specified element. Iterator returns the iterator over the elements of the set. The elements are returned in no particular order. Boolean remove removes the specified element from the set if it is present. Returns true if it contains the specified element. Int size returns the number of elements in the set. These are methods in the hash map class. Boolean contains key returns true if this map contains a mapping for the specified key. Boolean get returns the value to which the specified key is mapped, or null if the map contains no mapping for this key. Set key set returns a set containing the keys in the map. Boolean put adds the key value pair into this map, returns the previous value associated with the specified key, or null if there is no mapping for the key. Int size returns the number of key value pairs in this map. In the hash set class, a hash of the element is used to find its location in the hash table. In the hash map class, a hash of the key is used. The hash code method, which exists on all objects, calculates the hash code. The basic operations on hash set and hash map objects run in constant O1 time due to the hash table implementation employed by the class. The iterator that is returned by the iterator method of hash set does not order the objects returned. So there you have it, folks. The AP Computer Science saga has come to an end. I hope you enjoyed it and learned lots. Don't forget to be awesome.